So from the flat bar voltage, we can go up or down with biasing the gate voltage. So what we do now is we're applying more negative gate voltage. So today we're going to start with the MOSFET transistor basic operation. Then there is a second part to it, which is the second order effects, also quite interesting things. So from the basics of operation, I think that you for sure in some other lectures you were already discussing MOSFET transistors, you're quite familiar with that, but still we're going to start step by step, and some things I hope that you discover also new or solidify the knowledge. For the second order effects, I think that there are quite a few interesting topics, but the second order effects I will not start immediately today, but if we have enough time, then I will go to a lighter part, which is already about wafer fabrication, and this is what we're going to continue with, processing of the processing of the wafers to produce silicon-based devices, and then advanced technologies. Let's start with this part, MOS transistor operation. What I have prepared is an example, actually, that I like very much, which I call Microelectronics, which is a miracle and revolution. What somebody has called the most sophisticated and impressive engineering challenge of the mankind. And why I'm starting talking about it here, actually it would have fitted at the introductory part, but we are going to talk about MOSFET, and it's the development up to the MOSFET transistors that has led us through this exponential growth in microelectronics, where the computing power, thanks to the number of transistors per die, is exponentially increasing. Then the transistor size is increasing, and thanks to that fact we can increase the number of transistors per die. And what follows is that the cost of per transistor is exponentially decreasing. And to understand how great achievement it is, what it will be compared is this microelectronic trend to the trend in automotive industry. So if we look at the microelectronics and the Muhr's law, we will be still talking about it, but we look how this number of transistors per unit area is increasing over years. If we would like to trace such trend for automotive, let's take this Ford from the 1920s. What would be, sorry, 1913 it is, this picture from. So what would be the speed, the efficiency of liters per 100 kilometers, cost in dollars, mass, and the luggage of the boot room? Let's have a look what it would be today if we could follow the same trend. So the speed would exceed the speed of light. The efficiency, if we recalculate this, would be such that with 10 liters we could traverse the Milky Way. The cost would be just $1 femtodollar. The mass of the car would be comparable to DNA of the bacteria of E. coli. Actually, it would be even smaller. And the room for your luggage would be such that you could put in the solar system. So when we compare those two different words, it just shows it's really impressive what happens over the years, the last decades in the microelectronics. And because the main player of this consequence is the field effect transistor, that's what we are going to be talking here. If we look, and actually the whole planar technology, which is CMOSFET, where we have the N-channel MOSFET integrated next to P-channel MOSFET, creating this complementary pair where we can have circuits with very low power consumption, because basically the current between the power supply and the ground is, well, if we go to details and we have millions of inverters or of logic gates, then of course it comes to a considerable power, especially during switching. But basically there is no static current consumption in such inverter. And all that we have discussed before, so that means PN junction with diodes, metal semiconductor junction, bipolar transistors. This, even if in most cases for digital circuits we are not using it, let's say, consciously, but they exist also in those technologies as parasitic parts. So even if we are only dealing with the CMOS technology without special additional conditioning circuits, some sensing circuits that are integrated, still we will have those either diodes as parasitic and bipolar as parasitic, which we have to also understand what influence they make on the transistor and circuit operation itself. And very important, we have also this metal semiconductor junction, which can be, as we know already, metal ohmic or metal Schottky contact. And this we have every time that we contact with metal. So we see here several, just in this slide, we see several contacts to silicon, and each of them is exactly such contact, so which shows the importance, how important it is to tailor the right characteristics of the junction to have low ohmic and providing a good conductivity between the conductive interconnections and the silicon devices itself. So for MOSFET transistor, here, starting from the very basics, we have the geometry showing the top view and the cross-section. In the cross-section, let's start first. We can see those two at the bottom part of the picture. There are the N+ doping regions that will be for creating N-channel in between the drain and source, and that will be the N-channel transistor. We can also have P-channel transistor, where instead we have a bulk made of N-type material, and then the two islands are P+, and then with applying voltage at the gate, we create the P-channel at the transistor. Now, geometrically, two very important parameters which will appear in the transistor equation are the width and the length. The length is the distance between source and drain, and the width is how wide is the region. And sometimes, let's say if we want to just play or operate, let's say, with just the minimum technology features, the minimum length, but we want to increase the conductivity, reduce the resistance, then we increase the width of the channel, and like that we have the lower on resistance. So let's start with a very easy example where we have the MOSFET operating as a switch. In this case, where we have the N+ doping, if we would like that the switch is conducting, that we have a resistive path between the drain and source, what we have to do is apply voltage at the gate. This will attract the minority carriers from the P-type material, that means electrons under the gate, and the electrons form the charge sheet under the gate, which creates the N+ material. So characteristics of the material is N+ all along under the material, so under the gate material. So in fact, what we are doing is controlling the resistivity by applying voltage to the transistor. So on the left, what we can see is the off state switch, where there is no channel and we have certain off resistance. This off resistance, it's also important to have as high as possible. And here, what we have to point out, such switch, if we buy, let's say, also components in the catalog, which are solid-state switches, they will never be as good as mechanical relays. So the off resistance will be some hundreds of megaohms, but it will be still considerable leakage current that we have through. So it's not a perfect switch by no means. And then on resistance, of course, it will be dependent of the doping levels of the materials, both N and P-type. it will be dependent on the technological properties at the gate, the thickness of the gate, the material of the gate oxide, and polysilicon above, and of course the geometrical size of the transistor. And if we look on the plots as of drain voltage, so let's say here we have a drain on one side on resistance, on the other is the actual resistance to VDD. So that's our very simple circuit. Then we can look at the VD, the drain voltage as a function of VGS, and the drain current as a function of VGS. And we have here an example of seeing these non-idealities related to the leakage current. So when VGS is 0, then we would like that the switch is switched off. But we have certain leakage current, and because of the leakage current on the drain voltage, we will see something close to VDD, but not exactly VDD because it's minus the voltage drop of our resistance that we switch currents through or not. So the current is switched off, but still we have the leakage current, so there is some voltage drop. On the other hand, when we want to switch on the switch, then VDD is applied to the gate. So that means voltage that cannot exceed a certain value not to damage the transistor, but typically it could be for certain technologies 5 volts or 3 volts or 1.8 volts or lower depending on the technology node and the oxide thickness. So at that point, when VDD is applied high, then we see the drain current is approximately VDD divided by R, but approximately because we have certain drop due to the on resistance of our switch, which is also can be significant, and it depends on the balance in the circuit, what is the actual value of the R, the component that we add in the circuit, that determines what value of R on will be acceptable. So that's the very simple introduction to get started, and now we will go to the analog operation and go through the different regions of what happens as we sweep actually the gate voltage from low negative values to higher positive. And also similarly, we will analyze what happens in the p-channel MOSFET. And because even for working with digital circuits, which is switch which is simply on and off, but in fact there is also dynamic operation. So even just for working with digital circuits, we also need to understand the analog operation of the MOSFET transistor. So let's start with zero bias. So we have a here even simplified structure because I'm removing the drain and source. So we basically have something which is called also MOS capacitor. So this component exists where we have no drain and source, but we can see it also as a capacitor. But it's a perfectly nice example to show the conditions of what happens under the gate, and also to look at the band diagrams. And this is a perfect example to also explain what is the threshold voltage, how we define it. And then later we will see what the threshold voltage depends on, that actually the source and drain at that point are important to consider when we talk about the threshold voltage variations. So we have several materials, as you can notice in these pictures. We have the semiconductor at the bottom, then we have oxide, insulating, and then we have the metal or polysilicon gate material. Because of the different work functions, which we already looked at the topic at the occasion of the metal semiconductor junction, we see that every time, or even N-doped, P-doped interface for a diode, we see every time there is a difference in the work function, there will be band bending. So what we have here is that you need different amount of energy to remove electrons from the Fermi level of metal, which in fact is the just a single level here at the top of the valence band. And in the semiconductor, we have Fermi level, which is dependent on the doping. And those Fermi levels, because of the equilibrium conditions, they have, and no current flow, those Fermi levels have to be on single energy level. And because of that, we have the band bending on the semiconductor side, depending on the level of doping, depending on the type of metal, depending whether it's P or N-type doping, this bending will be different. And here, what we have as an example is that P-type semiconductor side, close to the gate, the band is bending down. So as if there were less holes available under the gate. We can tell that because the Fermi level, just under the gate, you can see that Fermi level and the intrinsic levels, they go close together. So that's like in undoped semiconductor. Next step is we go to the starting point. And the starting point is such voltage. It depends, again, on the materials, the doping, what type of metal, the type of the metal gate, and if it's polysilicon. But we can apply such voltage where the bands become flat. And here there is a table where you can see different values. For example, what would be for the aluminum, for the P+ polysilicon, because the gate can be made out of metal or polysilicon, or N-type polysilicon. And we can see that they are very different, and usually there will be the most suitable one that it's so that this flat band voltage is not really large, because we would like to almost not have to think about it in reality as operating transistors. So if we are talking about voltage thresholds which are a few hundreds millivolts, then it sounds almost ridiculous, the number of close to 1 volt flat band voltage. But so in the next analysis, these upcoming slides, what we will try to do is, okay, assume that it's something negligible, so that we almost not have to be talking about it. It's some starting point. But in fact, when we go into details, then please remember that we have this flat band voltage, and it's always part of the operation of the transistor that has to be taken into account. So from the flat band voltage, we can go up or down with biasing the gate voltage. So what we do now is we're applying more negative gate voltage than the substrate. That means that minus it's attracting the holes from the substrate under the gate. So we have the condition of accumulation. And the accumulation we can see on the band diagrams. The band diagrams are bending upwards in the P-type semiconductor, where we talk about the holes concentrations. You can see that the Fermi level, which is constant, it's further away from the intrinsic level, which is bending close to the interface, and closer to the valence band. So as if there was a higher doping, that's similar effect we can say, but in fact this is not controlled via doping, but via applying the potential. So this condition is called accumulation. And if we were talking about N-type semiconductor as a bulk, then what we would have is that for accumulation we have to apply positive voltage to attract electrons, because we would talk about electrons as the bulk majority carriers. So now we go in the opposite direction. So rather than for P-type substrate, rather than applying the negative, we apply the positive voltage. So if before it was accumulation, now it has to be depletion. So we are repelling the holes from under the gate. And that means the bands are bending in the opposite direction. So that means close to the gate, the semiconductor is more intrinsic-like, and we have less holes. So in P-type substrate, it will be with gate greater than the substrate, but in the N-type, it will be the opposite for gate has to be negatively biased, and then we're talking about repelling the electrons from under the gate in order to create this depletion region. And we have this interesting condition where at some point the bands are bending so far down that the Fermi level is exactly at the level of the intrinsic EI level. So it's as if it was really intrinsic semiconductor, and this is the edge of the weak inversion. So from now on, if we bend even further, then Fermi level is going to be above intrinsic level. So it's as if it was n-type material, because Fermi level is only going to get closer and closer to the conduction band. So this is weak inversion, and as we apply even further positive gate voltage, then we will go into moderate and strong inversion. And so we are already in the inversion condition, and here you can see that the Fermi level, it crossed over under the gate, the intrinsic level, and now it can only get closer and closer to the conduction band. And at some point, it will get so close to the conduction band that the difference of the Fermi energy just close to the gate interface, the difference between Fermi level and the conduction energy, is just the same. So in the arrows you can see B. As deep in the substrate, where we don't have the influence of the gate electric field, the difference between Fermi level and the valence energy. So A equal B, that's the condition that we call threshold. So now the inversion is strong enough that we talk about the transistor conducting. So very often in some very elementary discussions on the MOS transistors, we say that, okay, below threshold voltage it's not conducting, above it's conducting. Similarly, like with the diode, we can say that above 0.7 we have large current, but we see that it's gradual, and it's because of the characteristics that are then starting rapidly to increase. The current increase is maybe more rapid in the linear characteristics. That's why we talk about these characteristics points. But for threshold, if we take a book about extraction of the threshold, we will see that so nobody characterizing the transistor can actually measure the energies. So it's not like that the extraction happens, and there are also several recipes saying how the threshold voltage for the datasheet is being determined. So this is the theoretical view on the topic. And now what we see here is the summary of, just to repeat all the different conditions, which are also called operating modes under the gate. First of all, we have the flat band voltage, which can be anywhere positive, negative, and actually it's quite generous to have such a narrow band of the flat band because it can extend quite broadly in theory. We try, though, to make it as low as possible. On one hand, going to negative VGS, we have accumulation. Then if we go above to positive values, we have depletion. At certain point, going from weak inversion to the threshold condition, and then moving on to strong inversion. In case of P-channel transistors, so that will be for P-type bulk material, which is dedicated for N-channel transistors. For P-channel transistors, we have N-type bulk with electrons as majority carriers in the bulk and in the channel the holes, so we have to invert the hole characteristic. And now we add the next level of complexity, and what we can see here is also the source and the drain regions, the implants, for to obtain the N-channel MOSFET, also called NMOS. And we can see here in the picture A, the accumulation condition where the transistor is switched off, and even if we apply voltage between drain and source, we see only some leakage current, which is related on one hand to traps under the gate because there is some discontinuity of the material of silicon, and then there is a silicon dioxide gate. So there can be some charge transport along this border line. On the other hand, we have learned already about the diodes and the fact that in the reverse bias condition, the diode also has a certain current. And we have here the two diodes between p-type and n-plus materials, so that also contributes to the leakage current. In the figure B, we increase the gate voltage, something above threshold voltage, so we can comfortably speak about the channel that has formed. So we have the inversion of the substrate material under the gate. It becomes, rather than p-type, it becomes n-type, and we have the channel. And then if there is 0 voltage between source and drain, naturally there will be no current flow. And then the interesting thing that happens is when we observe the charge under the gate at the conditions where actually we apply voltage between gate and source. So what we can see is that the voltage between gate and the source is the same as the source is biased at the same potential as substrate. And we have normally the inverted charge as we will be going through this calculation. And on the right-hand side, we have the drain voltage, which is higher than the substrate voltage. And so the voltage across the gate towards the drain region, the difference in the voltage is much lower. And as long as it's still the difference of the voltage is above the threshold voltage, we have the inversion channel. But then we can imagine that as we increase the drain voltage, then the difference between drain and gate is going to be smaller and smaller. And at some point, even we can increase the drain voltage above the gate. And that's where also interesting things are going to happen. So this will be, we will come to that soon. So this is the condition. We have in the upper slide the so-called linear operation. So the current through the transistor changes linearly as we increase the drain voltage. And at some point, the drain voltage, it gets higher than the difference between gate and the drain. It becomes smaller than the threshold voltage difference. So we see that the inversion charge is disappearing under the gate. But because everything is surrounded with this symbolically shown with the dotted line, the depletion region, because we have negative reverse biased diodes, source bulk and drain bulk. So there is a depletion region. There is no charge in this area, so except for the inversion charge under the gate. So basically between there is no p-n junction, so to say, along the way of the charge carrier from one n-plus region to the other. So the electrons will be accelerated towards the drain, so the current arrow shows in the other direction. There are current flows from drain to source. But the majority carriers from the channel perspective are electrons, and the electron accelerated towards the drain, it's going to cross into this space charge region and still contributes to the current flow, but there is no more charge available, so that's why the characteristics of the drain current as a function of the drain source voltage show that in this so-called saturation region, the current remains constant. Intuitively is we can think of a waterfall. So the amount of water per unit time into the lake that falls down into the lake doesn't depend on how high is the waterfall. So if we now increase the VDS, and we see that the current remains constant, so basically we don't produce more charge carriers because the inversion charge, we cannot provide more unless we increase the gate voltage. So it doesn't produce more charge carriers, so the charge per unit time remains constant. The other type of transistor is the P-channel MOSFET. So let's go quickly through its analysis. So we have, in this case, N-type bulk. And the source and the drain are P-type, P+ islands. If we apply gate voltage greater than 0, then it attracts the electrons from the bulk, and we have the condition of accumulation. And whatever voltage we apply between drain and source, we see nothing except for leakage current. Sometimes might be significant, but sometimes, hopefully, negligible. Then, in picture B, we apply gate voltage, which is more negative, but it still didn't reach the threshold voltage, but the threshold voltage is negative. So we have to keep that in mind. So we decrease the gate voltage, and thanks to that, we repel the electrons from the bulk, from under the channel. And at some point, when we reach the threshold condition, so we are actually below in the gate voltage is negative and the threshold voltage is negative, and the gate voltage is negatively increasing, being already below the threshold voltage, then we have the channel. And if we apply then drain to source voltage difference, so we decrease the voltage of the drain, then we can see the current flow. At the beginning is the linear region, where the change in the drain voltage causes linear change in the current. But at some point, when the drain voltage and gate voltage, so the drain voltage goes much lower than the gate, then we have again the saturation condition. So at some point, we don't produce anymore the charge under the gate, but we have the depletion region, which maintains the current flowing through the transistor across the channel. This is the, let's say, we already saw the current as a function of the drain source voltage. We will come back to that one. This is the plot showing the current as a function of gate to source voltage for the accumulation, diffusion, and strong inversion. So we have overlapped characteristics on the regions that we have already seen before. And here I would like to stop for a moment to think about the how high the current can increase. So if we keep increasing gate voltage, is it going to increase into infinity? Well, obviously not. So what happens? What will happen if we keep increasing? Can something get damaged? Eventually, yes. It's possible that we apply too high voltage that the gate oxide breaks down. Anything else can happen? So even if it doesn't break, let's say that something else might happen before the gate oxide voltage is too high and it breaks. What else could happen? Well, we have some contacts contacting the source and the drain. There will be conductors which have finite resistivity, or not infinitesimally small. So there will be some voltage drop across them. So then the drain to source voltage that we have applied, which we assume constant for this characteristic, constant gate voltage, and constant drain to source voltage, for plotting one characteristic, and then we can plot family of characteristics at different drain voltages, but the drain voltage is going to change, for example. So the characteristic can get smoothed out. But what else can happen is we have the mobility as part of the component that decides, the parameter that decides about the current through the transistor. And the mobility degradation happens when we have very high density of charge carriers under the gate. So we have the scattering effects. and also the transconductance is going to be degrading because of that. So that's one of the saturation effects. The other is what already was mentioned, the series resistance in the drain. And then we have those destructive effects of gate oxide breakdown, and also at high current density, what we can have is, even if silicon has very high melting point, but the metallization around that is attaching to the drain and to source, it can melt because of much lower, so let's say aluminum, it's 660 Celsius degrees, and we might see some destruction because of that. So when we think about this other family of characteristics, drain to source voltage, or generally about operation of transistor, how it depends the drain current on the gate to source and drain to source voltage, we can look at the current equations to see exactly and to get the formula in just few lines. What we start with is the simple current equation. So the current is charge expressed in coulomb per unit time, seconds. So it's delta Q over delta T, which we can also rewrite since we know that our charge carriers have a unit charge of single electrons, and then we can calculate the number of charge carriers. So let's do like that. We have the Q times the charge concentration per unit volume times the volume. And I would like to separate it like that to talk about the volume, because then volume has several components. It's A, B, C, A, B, C. And we can rewrite it by using some specific geometrical properties of the transistor. So first of all, starting with width, that's the total width of the channel, so that will be one of the dimensions. And the inversion charge, Qinf, it's typically expressed as charge per meter square. Yeah, I think there is a little mistake. Times drift velocity, which is expressed in micrometers per second, and then in the units we should come to the sum of coulomb per microsecond. So let's start with drift velocity. How we define it, we remember, is the mobility times the lateral electric field. Qinf, the inversion charge, that's interesting because that's going to depend where we are at the channel and what is the channel voltage. So, but basically Qinf is going to depend on the capacitance of the oxide. So for MOSFET transistors, typically it's silicon dioxide. So depending on the thickness, the oxide capacitance is going to be different. And then the inversion charge, that's why I wanted to split into volume. It depends on the location in the channel, because we have applied certain drain to source voltage. So the amount of charge, the level of inversion is changing along the channel. So we have to make this variable of x. And we can make this intermediate step that we now express the current as the width of the transistor times the inversion charge, but as a function of the position along the channel. And the position can be between 0 and L, because the maximum length, the channel length is L, that will be the maximum, times the mobility and voltage per unit length of the transistor. If we now take the integral on the left-hand side, the current from 0 to L, and on the right-hand side from 0 to VDS, which is the maximum voltage that we see across the channel. So depending on the exposition, the voltage is gradually increasing. And we are talking always about the linear region. So the change is gradually linear. Then when we calculate this integral, we come to the expression of the drain current of the MOSFET transistor, which is the mobility, times the width over L, so width over length of the transistor, times the oxide capacitance, which is in farad per micrometer square. So when we remember that, then the units fit, times the gate to source minus threshold voltage times VDS and minus VDS square. And if we plot that, we would see such characteristics, which is, of course, non-intuitive. So the drain current is, as a function of the drain to source voltage, would be parabolic. But it's not the case. We know that in the reality, once we reach the pinch-off point, so the moment where close to the drain, the inversion charge just starts disappearing, and we keep increasing the drain to source voltage, then the current remains constant. So it looks like that. And we have those two characteristic regions, linear and saturation. And to move between the characteristics of the MOSFET transistor, this so-called output characteristics, what we do is change the gate to source voltage, and the current is increasing. This characteristic pinch-off point, where is the maximum of the parabola takes place, is equal to VDS. So the VDS at that point is equal to VGS, gate to source voltage, minus the threshold voltage. So this condition tells us whether, if we know what's the transistor threshold voltage, if we know what's gate to source voltage, and we know what's the drain to source voltage, we can tell if the transistor is in the saturation or in the linear operating region. And from the circuit perspective, that will be very important, because some circuits we really want to ensure that the transistor is operating in the saturation, because then we, like for example, in current mirrors, we know that if we have two transistors and one of them has gate and drain voltage equal, so it's certainly in saturation, and the other transistor has exactly the same gate voltage, then no matter what we apply at the drain, we know that the current is always the same because it's constant, except some second order effects that we're also going to discuss, which make it a bit more complicated. If we would like, to go one more time into this intuitive understanding of the linear and saturation region, I propose to have such example where we split the transistor into series connection of many transistors. It can be any number. For the fitting into just quick demonstration, let's make it 5. And they are all identical sizes, so basically the length is 5 times smaller than our original transistors, so we have 5 small transistors instead of 1 big. The threshold voltage in the example is 0.6 volts. Gate voltage applied is 1 volt, and we have 0 volt at the source. Now we apply at the drain 0.1 volt. So 0.1, with the quick analysis of the linear or saturation operating region, we see that the drain to source voltage is smaller than gate to source minus VTH. So we are in the linear region. And also, if we look at each single transistor, we can tell at the drain to source voltage, each of them will be such that we split equally this 0.1 volts, so it's 20 millivolts across every drain to source voltage. So for each we can say that what is VGS? VGS, it will be always a bit smaller for every next transistor, but always it's such that the gate source voltage minus threshold is still larger than drain to source. Now let's take the same structure, but let's apply a different drain voltage of 1 volt. So 1 volt, according to the recipe already shown at the output characteristics, the pinch-off point is when VDS is equal to VGS minus VTH. And here, drain to source voltage is 1 volt, and gate source minus threshold voltage is 0.4 volts. So we must be in saturation. And now when we analyze what happens at each little transistor. We see that the first transistor has, and let's assume, just make an assumption, it's very simplified view, but we can say, okay, what if we have, again, equally spaced, distributed the drain voltage along the channel, so we have 0.0 volts, then 0.2, 0.4, 0.6, 0.8 at each source of these little transistors. Then we can see that the gate to source voltage, so drain to source voltage in that case would be, if we simplify like that, 0.2 volts. And then gate to source voltage is decreasing. It's 1 volt, 0.8, and then for the third transistor it's already 0.6. And with that and drain to source voltage equals 0.2, when we have threshold voltage of 0.6, then we already would not be in the linear region. So that transistor, in fact, would be switched off if we think about it like that. But because it's a structure where we have everything enclosed in the depletion region, therefore the current is still flowing. So this is for just additional view on the analyzing the operating regions. And to solidify this knowledge, I have prepared several case studies. So let's go through them. And we start here with N-channel MOSFET. So what we have is, again, example transistor size we can give. But more importantly for this analysis is the threshold voltage. It's 0.5 volts. So what is the gate biasing mode? And what is the operating region? So for the gate biasing mode, I'll remind it's possible to have accumulation, depletion, and saturation, depending on what conditions are at the gate to source. If the source and bulk are connected together, we talk simply about gate to source voltage. And for the operating condition, it's similarly like we were already discussing, drain to source, whether it's greater or smaller than the difference between gate source and threshold voltage. So for both transistors, we can see that the gate voltage is the same, it's 1 volt. Obviously, it's greater than 0. It's also greater than the threshold voltage, so we are in strong inversion. Then for that's called strong inversion in this case, so we have a mistake. Regarding the operating region, so in the first case, there is certain current that produces voltage drop across the resistor, which gives 1 volt here. And if we know that it's 1 volt, then we can also calculate that this transistor is going to be in saturation. Now, what about the other one? In order to tell whether it's linear or saturation, we have to know the drain voltage. So with a twice smaller resistance, the drain voltage can be only higher. So what will be operating region in this case? So it's still saturation because the drain voltage is just higher. So the current is not changing. Second example. So here what is different is we look again on the gate biasing mode and the operating region. In this case, we have some different transistor. I should not put here the width and length because it might be confusing. It's just we have adjusted, let's say, resistor value and the transistor parameters so that we see here 0.1 volts and 3 volts at the gate. So the transistor is fully switched on. Again, it's in the strong inversion. And the drain voltage, when we look at it, 0.1 volt is certainly smaller than VGS minus VTH, so we are in the linear region. What about the case B? So the gate voltage here is lower than 0, so we are in accumulation, right? And there is a question about VDS. So just to be sure, we understand what accumulation means. What will be the drain to source voltage of this transistor? Or the drain voltage, simply. So the transistor is in accumulation, is not conducting, so it's completely switched off. Therefore, the drain is pulled up through the resistance to the upper power supply. We have case study 3 now. And in this case, we have p-channel transistor. So what about the first one? We have the 3-volt supply, 4 volts at the gate. What is the operating mode? It's accumulation, that's right, because gate voltage is much higher than the source and bulk, so we have the N-channel, P-channel transistor with N-type bulk, and the electrons are attracted under the gate. We have no channel. So there is no point in talking about operating region in this case. What about the case B? What can we tell about that? So let's have a look at the bulk. And when we see what happens there, we will not have to analyze so much further. So we have a forward bias diode between the source and the bulk. So this transistor is not at all correctly biased. So we have a N-type bulk in p-channel transistor, and then p region at the drain and source. So when p is higher than N, we have forward bias. And whatever we apply at the gate, we mainly see the current that goes between the source and the bulk. And then one more case study. So we have here N-channel and P-channel MOSFET. And now let's have a look at the gate to source voltage. In case of the N-channel, it's 1 volt. In P-channel, it's -1. So the level of inversion is exactly the same if we assume that the threshold voltage is the same. So in both cases, we have strong inversion. And the operating region is, in both cases, we can see maybe the transistors, to make it a real example, the transistors probably wouldn't be the same size. But let's assume, let's assume that it's the same size, in fact, but because that makes it interesting for the last questions. So we have, that's right. So we have 1 volt at the drain. So drain to source voltage is 2 volts. And in case of N-channel, it's 1 volt. So actually, it is realistic example if we think about it. If they were exactly the same width and length, what we see is that the voltage across the resistor is 1 volt in case of P-channel and 2 volts in case of N-channel. And looking at the transistor equations, if we have the same gate to source voltage, in both cases they are in saturation, so we can neglect VDS, and we have the same transistor sizes. Why the currents will be not different? Do you remember about the charge carriers mobility? So for holes, it will be much lower mobility than in electrons. That's why the currents that we see in this case, it's much smaller. And typically in the digital libraries, we will see that in an inverter, the size of the PMOS and NMOS transistors are not the same, but usually PMOS is much larger, so that to have the same on resistance as N-channel and symmetrical electrical characteristics of both sides switch, upper and lower switch on. One more thing to mention at this introductory topic to the introduction to MOSFET transistor is the depletion and enhancement MOS. So far we were talking about enhancement MOS, which are normally off. But what is possible to have either buying as a discrete component, but in the integrated technologies also, not always, but sometimes we have this option, is the depletion type MOSFET. And in depletion type, it's also called native transistor. It's normally on. So what we have to do, it's similar like JFET transistor. What we have to do is apply voltage in order to switch it off. And in that case, we have to apply more negative voltage so that to remove the existing channel from the transistor. Thanks for coming, and see you hopefully next week.
You're the signal in my static hum, a perfect match we've overcome. Wires cross but we still run, sparks fly in circuits